Hello, welcome back to Learn Economy. We have seen what autocorrelation is, the causes of autocorrelation, the consequences of autocorrelation, etc. So in this video, we are going to see the continuation of the same, the topic autocorrelation. Here we are going to discuss a test for autocorrelation. That means how can you detect autocorrelation in your model. Your model might not be suffering autocorrelation, but how can you be sure whether your model is away from autocorrelation or your model actually has a problem of autocorrelation? So in order to understand that, in order to detect autocorrelation, you have to use certain tests. There have been a wide variety of tests used by analysts to detect autocorrelation. We will be looking into these tests. Actually, we are not going into the mathematical aspect of this test, but what I'm planning is that I am planning to give you an idea with respect to the way in which each of these tests detect autocorrelation. Okay. So only if you are able to detect autocorrelation, you will be able to understand what is the cause of autocorrelation in your model, and only by detecting the cause of autocorrelation you will be able to solve the problem of autocorrelation. So I don't want to make this video very long by just giving you a very lengthy intro. So with this we are going to end the intro, and we are moving on to the video. Okay, you can use a wide variety of tests. There have been a multiple list of tests available for you, and you can choose any of these to detect autocorrelation in your model. You can either plot the residuals, or you can use Cochrane-Orchard procedure, or you can use durbin-watson test, or you can use a Lagrangian multiplier test, or you can go for first differences procedure. There is Ljung-Box test, then Godfrey test is there, Hildreth-Lu procedure is there, correlogram method is there, Morgan's I statistic is there. So I don't think that we are ending the test. There have been a lot of other tests coming nowadays to deal with the problem of autocorrelation, but right now what I'm doing is that I'm going to discuss these tests in its detail. When I say details, I'm not going to the mathematical part of the same. I'll be giving you an idea with respect to the way in which each of these tests are able to each of these tests is able to detect the problem of autocorrelation in your model. Okay, first of all, a plot of residuals. You have a list of your residuals, right? You will be having this, or just leave about it. You will be having u term in your model, that is error term in your model. So this plotting of the residuals is considered to be an easiest way to identify the problem of autocorrelation in your model. What you have to do is that you have to go for a scattered plot of your residuals. Okay, so this versus a time measurement for the observation will help you to identify whether you have autocorrelation in your model. If the data are independent, then the residuals will look randomly scattered. However, if a noticeable pattern emerges, then dependency is likely to be an issue. So you have to see whether your residuals are scattered in such a way to help you conclude that it is randomly scattered, or if it you have to see whether it has a noticeable pattern. If it has got a noticeable pattern, then it means that there is some kind of dependency or autocorrelation in the model. So that is one of the easiest way to find out whether your model suffers from the problem of autocorrelation. Next, we are going to some complicated methods to detect a problem of autocorrelation. When I say complicated, it is not that complicated when these methods are available as a package in your softwares, like many software like SPSS data, etc., are providing these kinds of tests. All these tests are built in many softwares like Stata, SPSS, etc. So you can use these by following certain steps. So I don't want to go much more detail into that. Just come back to Durbin-Watson's test. So what does it mean? Actually, it is a statistic. Okay, I am not going into the formula etc. of that statistic. You will be able to, you can directly test for this particular thing in your software. So just go to your software and see what are the steps involved. So this statistic would give you an idea regarding whether your model is actually facing the problem of autocorrelation. This test value is the indicator of that particular issue, or this test value will give you an idea with respect to autocorrelation in your model. So this value actually ranges between 0 and 4. Okay. Values between 0 and 2 indicates a positive autocorrelation. 2 actually indicates 0 autocorrelation, and values between 2 and 4 would give you a negative autocorrelation. So by analyzing the value of Durbin-Watson test and connecting it with the conclusions that we have given here, you can see whether your model actually has any problem of autocorrelation. Next, we have Ljung-Box Q test. This is also known as a portmanteau test, and this is actually used to test autocorrelation. And this test statistics of 9.06 actually corresponds to a p-value of 0.0024 or something. So there is a strong evidence of lag 1 autocorrelation. So here what you have to do is that you have to check your observation over time and see whether it is random or independent or something. All these things are actually statistic tests. So you will be having a table value, you will be having a actual value. So you will be comparing your actual value with the table value, and you will be rejecting or accepting or what your null hypothesis. Either it would be accepted or rejected or whatever it may be, depending upon whether your table value is more than your actual value, or whether your actual value is more than your table value, right? So all these things are statistics. Next, we have Cochrane-Orchard procedure. Again, this is available in many softwares. As such, it is available as such in many softwares. You can go for the same as well as in the case of Durbin-Watson test. So in this particular kind of procedure, what you have to do is that you are going for some iterative process. When I say iterative process, you are actually looking into the AR1 process. Then you are transforming your variable from the multiple regression model. Then you have to regress your YT star on the transform predictors by using the ordinary least square OLS method to obtain the estimates. And then you have to actually, this is an iterative process, a step-by-step procedure. Okay. Next, you have a Hildreth-Lu procedure. This is considered to be a more direct way of estimating your p-value. Then this, you can see that after establishing that your errors have some AR1 structure, or after establishing or after identifying that your model suffers from autocorrelation, then you can go for a set of steps like you can select a series of candidate values for your row. Then for each candidate value, regress YT star on the transform predictors using the transformation established in the Cochrane-Orchard procedures. Then you can retain the square of errors for each of the regressions. Then you can select the value which minimizes the square of errors as an estimate of your row. Another way to understand whether your problem suffers from autocorrelation is that you can go for the first difference. As I have already told multiple times, I have been telling this multiple times, right from the very day we have started this autocorrelation video. I have been telling that this is something which is to do with the time series data. So Here you can go for the first difference procedure as well to find whether your model has the problem of autocorrelation. Since your rho is frequently large for AR1 errors, many economists or many analysts, they suggested just setting your rho equal to 1 in the transform model of the previous two procedures. So this will give you some idea with respect to autocorrelation in your model. So that's all about the first difference procedure. Then you have Godfrey test. So here you are looking actually by considering a test statistic by here your null hypothesis that there is no serial correlation or there is no autocorrelation at all. And here, because the test is based on the idea of Lagrange multiplier testing, it is also known as LM test for serial autocorrelation. Okay, here also you will be having a null hypothesis and a what alternating hypothesis, and based on by comparing the table value and the actual value, you are able to make a decision with respect to whether you have to go for null hypothesis or alternative. Next, correlogram. Correlogram, this too is an easiest method. It's a chart of correlation statistics, right? So here, for example, you can plot the sample autocorrelation, which is known as a correlogram. This is considered to be a very easy tool, right? As in the case of as in this is considered to be the very easy tool. As just by looking into the diagram, you will be or diagram or chart, you will be able to understand whether your model has got some kind of autocorrelation or not. So autocorrelation should be near zero for any and all 10 black separations. If non-random, then one or more of the autocorrelation will be significantly non-zero. So that's all about correlation. With that, we move on to the Morgan's I statistic, which is again another statistic to test for autocorrelation. It measures how one object is similar to others surrounding it. So if objects are attracted, that means that if there is autocorrelation, it means that observations are dependent on each other, right? Or if this violates the basic assumption of statistic independence of data, or in other words, you can see that the presence of autocorrelation renders most statistical tests invalid. This Morgan statistics, it is one of the important ways to test for autocorrelation. This is mainly used with respect to spatial autocorrelation, or this is used for multi-directional or multi-dimensional autocorrelation. So you will be able to use, you will be able to have some kind of patterns in complicated data sets. The value would be lying between -1 and +1, as in the case of usual correlation. Here -1 shows perfect clustering of dissimilar values. 0 shows no autocorrelation at all, and +1 means that a perfect clustering of similar values. Okay, so that's all about Morgan's I statistic. I think I am able to give I could give you some idea with respect to the various tests which could be used for autocorrelation, since you people are not that much required to focus on the statistic part of that. I'm not looking into that, and what I wanted is that I just tried to give you an idea with respect to different tests which could be used to detect the problem of autocorrelation. I hope I have done that. If you have any doubt, or if you want me to do any kind of test in specific, the details of any test, you can comment it in the comment box. So that's all for today. You are free to do that. Okay, you can you are free to comment your suggestions, the topic you want, etc. in the comment box. That's all. Please like, share and subscribe to this channel for more videos, and you can be a part of my Telegram group and Telegram channel to discuss your doubts. I'll be providing the links of both my Telegram channel as well as my group in the description box. You can be the same, and you can make discussions in the group as well. So that's all for today. Thank you.